Welcome back, networking enthusiasts. In this video, I will show you how to upgrade your WireGuard site-to-site hub-and-spoke network from using static routes to OSPF dynamic routing. I will tell you what dynamic routing is and what are its benefits. We'll talk a bit about OSPF, just enough to get you started. We'll demo everything using a topology from our previous video. As a bonus, we'll try to distribute our traffic among multiple links with ECMP and simulate a link failure to see if our network can recover. My name is Philip. Let's get started. This video is part 2 of building a WireGuard hub-and-spoke network with dynamic routing series. If you haven't already, I encourage you to watch the first part of the tutorial, as that will be our starting point. Where we left off is we have two sites connected to a central hub using WireGuard tunnels. Important thing to mention is that the hub has two WireGuard interfaces. One forming a point-to-point link with the first site and another forming a point-to-point link with the second site. Each tunnel is configured to have quad zeros in the allowed IPs section that allows it to route any network via that link. The question is, why go through all this trouble to have a separate WireGuard interface on the hub, point-to-point links and quad zeros in the allowed IPs section? We could just do WG quick script and have everything ready in few minutes. That's true, but then your network will be fixed, predefined. Using static routes is a good option for small networks. However, if you'd like your network to be scalable and able to dynamically adapt to changes, you need to go with dynamic routing. Dynamic routing is a technique in which routers are capable of dynamically learning, updating and sharing information about network routes. Unlike static routing, where network administrators manually configure the routing tables on each router, dynamic routing protocols automate the process of route determination based on real-time information. The OSPF routing protocol that we'll be using today allows you to automatically discover neighbors and learn new routes. It detects and responds to link failures. If a link goes down, OSPF routers can quickly recalculate the routes and update their routing tables, reducing the time it takes for the network to adapt to changes. Moreover, OSPF calculates the shortest path to reach each destination in the network. The shortest path is determined based on the cost associated with traversing each link. This ensures that routers select the most optimal path, leading to efficient use of network resources. On top of that, OSPF allows your network to be more scalable. You can increase network complexity without manual intervention. This reduces the administrative overhead associated with managing static routes. Network administrators don't need to manually update routing tables on each router whenever there is a change in the network. Let's get to business as we have lots of ground to cover. We'll use Bird, that's one of the best routing software available for Linux. It supports multiple routing protocols. What we'll use today is OSPF, as it's a popular choice for internal routing. OSPF is a very powerful, feature-rich and complex protocol. By no means this is not an OSPF tutorial. Today we'll just scratch the surface, enough to get you started. First, let's install Bird. Then let's remove all the static routes that we've set up last time, so we have a clean slate. I'm removing IPv4 static routes on the hub, removing static routes on node 1 and node 2. Let's get rid of IPv6 static routes as well. I will remove Bird's default configuration, as we'll be doing everything from scratch. Let's start with hub initial configuration. First, we need to provide a router ID. I will use 169.254.0.1. This is not an IP, but a 32-bit number written in IP notation. Bird supports various routing protocols that can exchange routes between each other. One that most protocols rely on is called device. It's not a real routing protocol, but it's used to get information about network interfaces from the kernel. For OSPF to work, we need to have device protocol enabled. We just type protocol, followed by protocol type, that's device, and then optional parameters inside the braces. Next, let's set up our OSPF instance that will handle our dynamic routing. Let's start with the protocol keyword as we are defining a new protocol, followed by OSPF to indicate we want to use OSPF. Mind, if you don't specify protocol version, it will default to version 2 that only supports IPv4 traffic. Next, let's specify the name. I will name it WG4 as this particular section will handle IPv4 traffic only. Our network can be split into multiple areas to reduce the amount of resources consumed for exchanging routing information. Mind that area 0, also called the backbone area, interconnects all other areas and is mandatory. In our case, we'll set up just the area 0. Inside that area, we need to define the interfaces to talk to other OSPF routers on the network. Our neighbor routers that will exchange routes with are node 1, reachable over interface WG0, and node 2, reachable over WG1 interface. We can simplify the notation with an asterisk like this. In other words, we want all WireGuard interfaces to participate in OSPF routing. Every interface that we specify here will periodically send OSPF hello messages. This allows neighbors to be discovered dynamically. Every router maintains an identical copy of a database describing the network topology called the link state database. The neighbors exchange their parts of the link state database and keep it identical by floating updates to ensure that each router detects all the changes. Okay, our router ID is set, device protocol is enabled, OSPF protocol is enabled for IPv4, we have area 0 defined, WG0 and WG1 interfaces participate in OSPF. Let's save the configuration and run Bird2, that's the command line tool to manage Bird daemon. Let's reload the configuration with configure command and check which protocols are running. There's the device protocol and also our OSPF IPv4 protocol named WG4. Our router is alone. It could not find any other OSPF neighbors. If we look at our OSPF topology, there is only a single router with ID 169.254.0.1 that belongs to area 0. Let's display our OSPF neighbors with the show OSPF neighbors command. There are no neighbors. That's to be expected. Let's configure node 1 and node 2 to be hubs neighbors. We'll set the router ID to 169.254.0.2. Let's add device protocol and add an OSPF protocol named WG4. Define area 0 and define the WG interface that will be used to communicate with the hub. We need our 10.x private networks to be advertised by OSPF to other nodes. There are multiple ways to do it. The simplest way to advertise a network is to add the network interface we want to advertise to the area. I will check which interface is pointing towards the private network. It's ETH2. Let's add it to the configuration. Finally, let's fix node 2 router ID. Save the configuration. Run our Bird command line tool and reload the configuration. Let's list our OSPF neighbors. Both node 1 and node 2 show the hub as the neighbor, reachable via WG0 interface. If we list OSPF neighbors of the hub, we have two neighbors. Node 1 with router ID 0.2, reachable via WG0 interface, and node 2 with router ID 0.3, reachable via WG1 interface. Stateful is a final state that indicates that OSPF adjacency is fully established. Link state databases are in sync and node is ready to route traffic. D-time is the dead interval, and it is the time a router waits without receiving a hello packet from a neighbor before declaring the neighbor as unreachable or dead. If the router does not receive a hello packet within the dead interval, it assumes that the neighbor is no longer reachable. If we display our OSPF topology, we can see that there are three routers that belong to area 0. First one with ID 01 has distance 0. That is us, the hub. It has two neighbors, a router with ID 02 and 03. Then we have router 02 with distance 10. That has a single neighbor, that's the hub. And router ID 03, also with distance 10, that also has a single neighbor, the hub. 10 is the default distance for single hop. Finally, let's list our Bird routing table. Master 4 is the Bird's main routing table for IPv4 traffic. We can see the hub is aware of 10.1 network. It can reach it via 0.2 IP over the WG0 interface. Hub is also aware of 10.2 network, reachable via 0.3 IP over the WG1 interface. It learned about those networks from our WG4 OSPF instance that's up since 9:55 p.m. Asterisk indicates that's the best route, as you can have more than one route available, especially if you are using protocols like BGP. We also see the preference and distance. Preference is protocol specific. Protocols with higher preference will be preferred. For example, static routes have this value set to 200, OSPF default is 150, BGP is 100. It means that static routes will be preferred over OSPF, and OSPF will be preferred over BGP, and so on. I did tell you about OSPF hello messages. Let's see them live. I will perform TCP dump on WG0 interface. We discovered that both hub and node 1 are sending those periodic hello messages to 224.0.0.5 multicast group. Those messages contain router ID, area number, but also timers. A hello timer that indicates how often a hello message is sent, and dead timers that indicate time a router waits without receiving a hello message to consider a neighbor unreachable. For faster link failure detection, it's recommended to tune down those values, unless we want to wait 40 seconds to detect a neighbor down. For sub-second failure detection, we can use BFD protocol. I can show you how that works in a separate video. Before we proceed further, let's do some cleaning. ETH2 interface on node 1 and node 2 points to a client network. There will be no OSPF routers there. We should not send OSPF messages via ETH2 as we won't form a neighbor relation there. We just want to advertise those networks to OSPF. There's a special switch called stub. If we set it on an interface, it will not listen to any OSPF packets or send any OSPF messages out. Just to reiterate, all interfaces that you enter here will be used to form neighbor relations, and also those networks will be advertised into OSPF unless it's a point-to-point link. If we want a network to be advertised into OSPF, but don't want the interface to send or receive hello messages, just put stub flag on the interface. Node 2 has two private networks. Let's advertise the second one. Let's reload the configuration. Now let's go to the hub and list Bird routes. Do you see that? Hub did learn about our network immediately, as did Node 1 and Node 2. That's the beauty of dynamic routing protocols. Moreover, you can filter the routes, calculate different routes if a route fails, use equal cost path for load balancing, inject routes from one protocol to another protocol, and so on. Okay, if we go back to the hub and try to list our operating system routing table, we'll discover that it does not have those new routes available. Why is that? Bird maintains its own routing table called master4 for IPv4. In order to synchronize the kernel routing table with Bird's master table, we need to add another protocol called kernel. We do it by specifying protocol kernel. Inside, we set the IPv4 channel. The channel binds protocol to a routing table. Here, we can specify which routes we want to send or receive. As we don't want to import any routes from the kernel to Bird, let's put import none. We want to export all the routes from Bird to the operating system, so let's put export all. Now let's reload Bird configuration. We'll discover the kernel protocol is up. Now let's check our operating system routing table. Our 10.x routes are there. They have been injected by Bird. Let's add the kernel protocol to node 1 and node 2. Let's reload the configuration and check the routes. The routes are there, even more than once. If we go to VM3 inside the 10.3 private network, behind node 2, and try pinging VM1 inside the 10.1 private network behind node 1, the connection works. Let's do some more cleaning. First of all, we see some duplicate routes. For example, 10.1 route is directly attached. We see the same route learned from OSPF. We can easily filter out these routes so we have only the routes for the network that's directly connected. We don't need to learn about a route that we already have. Let's go to node 1 and open the configuration file. In the OSPF section, let's define IPv4 channel that binds the protocol to the routing table and define that we want to import all routes except our own route that's directly connected. Let's reload the configuration and list the routes. Our duplicate route to 10.1 network is gone. It has been filtered out. Let's repeat the same step for node 2. I will open the configuration file and update OSPF IPv4 channel to import all routes except the two that we own. Let's reload the configuration and check our routing table. Looks good. Let's also set up OSPF to route our IPv6 traffic. We'll follow the same steps. First, let's go to the hub. I will clone the kernel protocol section and just set the channel to IPv6. That will synchronize the master 6 table that holds IPv6 traffic with the kernel IPv6 routing table. I will also clone the OSPF protocol section, change the protocol version to 3 as that version supports IPv6 and name it WG6. Let's reload the configuration. Our OSPF version 3 protocol named WG6 is there. It has no neighbors yet. Mind that OSPF version 2 that we did use for IPv4 and OSPF version 3 that we use for IPv6 are not compatible. Those are two separate protocols. Moreover, OSPF version 3 is using an IPv6 multicast address to communicate. The second kernel instance for the master 6 table is also there. Let's move to node 1. Clone the kernel protocol section and set the channel to IPv6. Let's clone the OSPF protocol section, change OSPF version to 3, change the name to WG6 and set the channel to IPv6. I will also update directly connected networks to FD1 to reflect IPv6 network on node 1. Now, let's reload the configuration. Let's move to node 2. Open Bird configuration, clone the kernel protocol section and change the channel to IPv6. Let's clone the OSPF protocol section, change OSPF version to 3, change the name to WG6 and set the channel to IPv6. I will also update directly connected networks to FD02 and FD03 to reflect IPv6 network on node 2. Finally, let's reload the configuration. Let's go back to the hub and list protocols. We can see kernel for IPv6 and OSPF for IPv6. Now we can see IPv6 neighbors present under WG6 instance. Mind that the router IPs are IPv6 link local addresses. Let's list our routes. Nice. We have both IPv4 routes under master 4 table and IPv6 routes under master 6 table. Let's check the routing table in the operating system. We can see FD private networks injected by Bird's kernel protocol. Let's do a connection test. I will go to VM3 and ping VM1. Works. I did promise you some bonus content. Let's start with ECMP, that stands for Equal Cost Multipath. This technique is used to distribute traffic across multiple links with equal cost. The main purpose of ECMP is to provide load balancing and redundancy in network environments. This will enhance network performance, provide fault tolerance, and make better use of available network resources. We'll add a second link between hub and node 2. This will allow the traffic to flow via both links. Distribution of traffic is done using a hashing algorithm that takes into account specific attributes of the packet, such as source and destination IP addresses and ports. This ensures that packets belonging to the same flow or session are consistently sent over the same path, maintaining proper sequencing. In our case, the links are equal in terms of bandwidth and delay, however, they don't have to be. You can configure ECMP over unequal links and fine-tune the amount of traffic over each link. Let's start with adding a second link between the hub and node 2. I will go to the hub and copy the WireGuard configuration from the existing link. Let's update the listening port and endpoint port to 60,033. I'm reusing the same IPs from the public network. In a real-life scenario, you would have a link with different IP from a different ISP. Now let's add a new interface. Configure IP address for the link. I can reuse the same IPs on both ends as this is a point-to-point link. Now let's set our WireGuard configuration with wgsetconf command and finally bring the interface up. Let's repeat the same steps on node 2. Copy the configuration, update listening ports, add new interface, set up the IPs. Now let's set our WireGuard configuration with wgsetconf command and bring the interface up. If we go to the hub and show Bird's routing table, we can see that 10.3 and 10.2, as well as FD02 and FD03 networks are available via two paths. Let's show the operating system's routing table. It also shows 10.2 and 10.3 networks available via ECMP. Let's check IPv6 routing table. Same story here. FD02 and FD03 networks have two paths available. One via WG1 and second via WG2. We can try pinging the other end of the tunnel via WG1 interface and via WG2 interface. Let me show you how it works in practice. First, let's change the default multipath hash policy to make the decision about the multipath split not only based on IP, but also TCP/UDP ports. Next, let's start the IPTraf tool to monitor interface utilization on the hub. I will select General Interface Statistics. This will show us the interface name as well as the interface utilization. I will go to VM3 and start hyperserver listening on port 1111. I will start yet another hyperserver on VM3, but this time listening on port 2222. Now let's run some traffic from VM1 to VM3, port 111. If we go back to the hub, we can see that WG link is fully utilized. Let's run a second hyper session to port 2222. Do you see how traffic is split across two links? WG1 and WG2? Nice. Finally, let's see OSPF in action. We'll ping VM2 from VM1. The traffic will go from VM1 to node 1, then to the hub, from hub to node 2, and from there to VM2. Mind that from hub to node 2, it can go via either this tunnel or this tunnel, as this is an ECMP route. Let's go to the hub and check the routing for VM2. VM2 is reachable via both WG1 and WG2. Let's start the ping. I'll go to node 2 and check which interface the traffic is arriving at. Okay, the ICMP traffic arrives via WG1. Let's bring this interface down. Now let's go back to the hub and see what happened with our routing table. Route via WG2 is still present. Let's check OSPF neighbors. That timer is decreasing. It means we are not getting hellos on that link. Let's wait a few more seconds. Neighbor is gone. Let's check the route one more time. Only one path is available. Let's go back to VM1. Traffic is still flowing, but this time via a different link. Of course, the default dead timer is 40 seconds. You could change hello interval to 1 second and dead timers to 3 seconds. Or if you require rapid recovery, use BFD protocol to detect link failures. I hope you've enjoyed today's demo on how to make your site-to-site VPN network more scalable and resilient to failures. We've just dipped a toe into the topic, but based on that, you can experiment further. You should definitely add authentication to protect your OSPF traffic and fine-tune the timers. Like I said earlier, OSPF is a complex protocol with lots of bells and whistles, but it's also very powerful.